The proposed configuration of using a single transformer to step down from a 480 volts generator to supply both three-phase 240 volts and single-phase 120 volts loads is unique and requires careful analysis. It is crucial to ensure compliance with all applicable electrical codes and safety regulations. Note that oversizing the transformer, while seemingly providing headroom, may introduce additional system losses and inefficiencies that need to be considered. Using a 75 kV transformer is a reasonable approach given the limited three-phase load and the estimated single-phase load. However, it's important to acknowledge that the transformer's single-phase capacity would be severely underutilized during typical operating conditions. The three motors, each consuming approximately 10.4 kVA, will have a combined three-phase load of 31.2 kVA at 240 volts. This load falls well within the capacity of a 75 kV transformer. The single-phase load is estimated at 40 amps, which equates to 9.6 kVA at 240 volts. This load is also within the transformer's single-phase capacity when derived from the 240 volts winding. A 150 amps breaker provides adequate protection for the transformer's secondary. However, it is highly recommended to use a breaker with an adjustable trip setting to prevent any nuisance tripping due to inrush currents or minor overloads. The three-phase coil amperage is approximately 38.75 amps, which is within the transformer's rated amperage for the three-phase portion of the load. The single-phase coil amperage is approximately 98.75 amps, which is also within the transformer's rated amperage for the single-phase portion of the load. Due to the non-standard nature of this application, it is highly recommended to consult with a qualified electrical engineer or a manufacturer's representative who has experience in such transformer configurations. They can provide valuable guidance and validate the design to ensure safe and reliable operation. As alternative options, firstly, consider using three separate transformers. One 480 volts to 240 volts transformer for the three-phase load, and two 240 volts to 120 volts transformers for the single-phase load. This approach offers greater flexibility, better load balancing, and potentially higher efficiency. Secondly, a 480 volts to 120/240 volts autotransformer could be used to provide both three-phase and single-phase power from the generator's 480 volts output. An autotransformer can sometimes be a more cost-effective and efficient solution, but careful consideration must be given to isolation and safety. Now, let's discuss transformer sizing in more detail. When selecting a transformer for this application, it's crucial to consider not only the connected load but also the potential for future expansion. A 75 kV transformer appears adequate for the current load, but if there's a possibility of adding more motors or increasing the single-phase load, a larger transformer may be warranted. It's also important to factor in the transformer's efficiency. Transformers are not 100% efficient, and some energy is lost in the form of heat. The efficiency of a transformer typically ranges from 95% to 99% depending on its size and design. The lower the efficiency, the more energy is wasted, and the higher the operating cost. Consider the transformer's impedance. The impedance of a transformer is a measure of its opposition to the flow of alternating current. A transformer with a high impedance will limit the fault current, which can help to protect the electrical system in the event of a short circuit. However, a transformer with a high impedance can also cause voltage drop, which can affect the performance of the connected equipment. Also, when calculating the load on the transformer, it's essential to consider the power factor of the loads. The power factor is a measure of how effectively electrical power is being used. A power factor of 1 indicates that all of the electrical power is being used to do work, while a power factor of less than 1 indicates that some of the electrical power is being wasted. Motors, in particular, typically have a power factor of less than 1. This means that they draw more current than they need to do work. When calculating the load on the transformer, it's necessary to divide the kilovolt amps of the motor load by the power factor to get the actual kilovolt amps load. Now, regarding motor load considerations, Each of the three motors consumes approximately 10.4 kV amps. This is based on the horsepower rating of the motor, which is 7.5 horsepower. To convert horsepower to kilovolt amps, you can use the following formula. Kilovolt amps equals horsepower times 0.746 divided by the efficiency of the motor divided by the power factor of the motor. The efficiency and power factor of a motor can typically be found in the motor's nameplate. The total three-phase load of the motors is 31.2 kV amps, which is well within the capacity of the 75 kV amps transformer. However, it's important to note that motors can draw a significant amount of current when they start. This is known as inrush current. The inrush current of a motor can be several times its running current. The transformer must be able to handle the inrush current of the motors without experiencing excessive voltage drop. Now turning attention to single-phase load estimation, the single-phase load is estimated at 40 amps, which is equivalent to 9.6 kV amps at 240 volts. This load consists of scales and lighting. It's important to ensure that the transformer is properly sized to handle the single-phase load without overloading it. If the single-phase load is too high, it can cause the transformer to overheat and fail. Regarding transformer secondary protection, a 150 amps breaker provides adequate protection for the transformer secondary. The purpose of the breaker is to protect the transformer from overcurrents such as those caused by short circuits or overloads. The breaker should be sized to protect the transformer without nuisance tripping. Nuisance tripping occurs when the breaker trips unnecessarily, interrupting power to the load. To prevent nuisance tripping, it's recommended to use a breaker with an adjustable trip setting. The trip setting can be adjusted to allow the breaker to withstand momentary overloads such as those caused by motor starting without tripping. Now let's discuss coil amperage calculations in more detail. The three-phase coil amperage is approximately 38.75 amps. This is calculated by dividing the three-phase kilovolt amps load, which is 31.2 kV amps, by the line-to-line voltage, which is 240 volts, and then dividing by the square root of 3. The single-phase coil amperage is approximately 90.75 amps. This is calculated by dividing the single-phase kilovolt amps load, which is 9.6 kV amps, by the voltage, which is 240 volts. It's important to ensure that the coil amperage is within the transformer's rated amperage to prevent overheating and failure. Because this is a non-standard transformer application, it's highly recommended to consult with experienced professionals. A qualified electrical engineer or a manufacturer's representative with experience in non-standard transformer applications can provide valuable guidance and validation. They can help to ensure that the transformer is properly sized, protected, and installed to provide safe and reliable operation. They can also help to identify any potential problems and recommend solutions. Remember also the NEC Article 450 covers transformers. Article 450.3 addresses transformer overcurrent protection. For transformers over 600 volts, primary side protection is typically set at 125% of the transformer's rated primary current. Secondary protection, if provided, is also typically set at 125% of the rated secondary current. For transformers 600 volts and under, the primary protection can be up to 250% of the rated primary current if the secondary protection is at 125% or less, or the primary protection can be 125% if there is no secondary protection. These percentages are based on specific conditions and transformer impedance, so always refer to the NEC for exact requirements. NEC Table 450.3 provides guidance on transformer overcurrent protection based on voltage and impedance. Regarding grounding and bonding, proper grounding and bonding are essential for safety. The transformer's neutral point should be grounded according to NEC 250. The equipment grounding conductor should be sized according to NEC 250.122. Bonding all metallic parts of the transformer enclosure and the electrical system helps to create a low impedance path for fault currents, which helps to trip over current devices quickly and safely. Also note that transformers generate heat during operation. Adequate ventilation is essential to prevent overheating. Follow the manufacturer's recommendations for ventilation. Do not block ventilation openings. Consider the ambient temperature when selecting a transformer. High ambient temperatures can reduce the transformer's capacity. Regarding transformer installation, install the transformer in a dry, clean location. Protect the transformer from physical damage. Ensure that the transformer is securely mounted. Follow all applicable codes and standards. Always obtain the necessary permits and inspections. Remember that qualified personnel should perform transformer installations. Work on electrical equipment can be dangerous and should only be performed by qualified electricians or other trained personnel. If you are not qualified, do not attempt to install or work on electrical equipment. Now let us explore alternative solutions in more detail. Firstly, using 3 separate transformers provides greater flexibility and redundancy. If one transformer fails, the other 2 can continue to operate. This can be important for critical loads. Secondly, 3 separate transformers also allow for better load balancing. This can help to improve the efficiency of the electrical system and reduce voltage drop. Thirdly, 3 separate transformers can also be more cost-effective in some cases. If the single-phase load is small, it may be less expensive to use 2 small single-phase transformers than to use a single large transformer. However, using 3 separate transformers also has some disadvantages. It can be more expensive to install 3 separate transformers than to install a single transformer. It can also take up more space. A 480 volts to 120/240 volts autotransformer is another alternative. An autotransformer is a type of transformer that has only one winding. The winding is tapped at different points to provide different voltage levels. An autotransformer can be more efficient than a traditional transformer because it does not have separate primary and secondary windings. An autotransformer can also be smaller and lighter than a traditional transformer. However, an autotransformer does not provide electrical isolation between the primary and secondary circuits. This means that there is a direct electrical connection between the input and output voltages. This can be a safety hazard in some applications. Regarding harmonics, nonlinear loads such as electronic ballasts and variable frequency drives can generate harmonics. Harmonics are currents and voltages that are at frequencies that are multiples of the fundamental frequency. Harmonics can cause a variety of problems, including overheating of transformers, reduced power factor, and interference with other electrical equipment. If there are significant nonlinear loads, it may be necessary to use a harmonic filter to reduce the harmonics. Also note that transformers can generate noise due to the vibration of the core and windings. The amount of noise generated depends on the size and design of the transformer. If the transformer is located in a noise-sensitive area, it may be necessary to use a sound enclosure to reduce the noise. Consider future load growth. When selecting a transformer, it's important to consider the potential for future load growth. Choose a transformer that is large enough to handle the current load and the anticipated future load. It is also important to consider the available space for the transformer. Choose a transformer that will fit in the available space. Finally, evaluate the total cost of ownership. Consider not only the initial cost of the transformer, but also the operating costs, such as energy losses and maintenance costs. Choose a transformer that has a low total cost of ownership. Remember to always consult with qualified professionals. Electrical work can be dangerous, and it's important to consult with qualified professionals to ensure that the work is done safely and correctly.